Welcome to the third video about the Whitebox challenge of the RHme3 Qualifier. In the first video, we just had a first reverse engineering look at the binary and figured out how it works and how this big switch case statement in the jump table is implemented. And then in the second video, we used that knowledge to trace all the functions and start to reverse engineer single sections of it. I also told you that at the same time people were talking in IRC about this challenge and saying something about AES, and at first I didn't believe it. And also a friend was telling me or hinting me I should look into Whitebox because Whitebox is a thing. And so towards the end of the video we actually found proof that it's actually AES, or it's very likely to be AES that is implemented in the binary, as well as learning about what Whitebox cryptography is. And this is basically where we left off. So now in this video I want to go over more of my notes and the next steps I took after I heard that Whitebox exists and that I assume it's AES. Obviously, one of the first things I did was Googling what Whitebox actually is. And I showed you already the site in the very first video, but let's quickly recap. Whitebox cryptography is for protecting cryptographic keys in software applications. Cryptography is increasingly deployed in applications that are executed on open devices, such as PCs and tablets and smartphones. The open nature of these systems makes the software extremely vulnerable to attacks, since the attacker has the complete control over the execution of the platform and the software implementation itself. This means that an attacker can easily analyze the binary code of the application and the corresponding memory pages during the execution. The attacker can intercept system calls, tamper with the binary and its execution, and use any kind of attack tool such as IDA Pro, debuggers and emulators. Such an attack context is denoted as Whitebox attack. And the challenge that Whitebox cryptography aims to address is to implement cryptographic algorithms in software in such a way that cryptographic assets, basically the key, remain secure even when subject to Whitebox attacks. So when I read this for the first time, it made kind of sense. Okay, so we have AES and it's a symmetric cipher. And so it uses the same key for encryption that it uses for decryption. So if you want to implement AES in a software that is shipped to a client, the client can just reverse engineer the binary and extract the key. And so Whitebox cryptography kind of tries to protect that, tries to obfuscate that. In theory, you could say that already like crypting the binary or obfuscating the binary is already a step in that direction to hide or obscure the fact that AES with this key is used. But Whitebox cryptography goes a step further, that it actually designs or modifies the algorithm, the AES algorithm, in a way that it still performs AES, but it doesn't match the typical steps that we see, for example, on Wikipedia. And here's also a figure that depicts the conceptual high-level overview of Whitebox cryptography. So you have like a very defined algorithm. I'm not sure what algorithm this is depicted here in this case, but so theoretically you always have as input the ciphertext and the key, and that produces then in a well-defined algorithm the plaintext. But then you kind of apply some random configuration and you completely mess up the stuff and you get something weird on the right, and the key is kind of embedded already in these steps. When I first heard about this, I thought, okay, I think I get it. That makes sense. That's quite interesting. And so with this knowledge and knowing that it's AES and that it's obviously AES somehow obscured into the binary, I was starting to think about how this could maybe be implemented. And I kind of refused to just read papers on it. There are Whitebox AES papers out there that describe different techniques how to implement something like this. And I was really lazy. I didn't want to read them, and I felt like I was so deep into this already with reverse engineering, and I understood the binary more and more that I felt like, dude, I'm on a way to understand this actually myself, like rediscover what Whitebox crypto basically is without having to read the work of other people that just describe how it works. And I thought this is a cool opportunity to like try this out. Like you kind of know where it's going, but you don't really know the way. Let's continue with reverse engineering and thinking about this like a scientist would do instead of just reading the papers. And that kind of also was a problem why it in the end didn't succeed, but more about this then in the latest video. So in this video, I want to show you more of my notes and basically just go over the different stuff that I wrote down here and tell you what I thought about them. The intention here is just to show you what was going on in my head and show you how I kind of try to achieve this and understand this. Obviously, this didn't quite let me to the solution, and I kind of gave up on this at some point, but I still think for some people it might be interesting to see what I was thinking, and maybe if you are actually very knowledgeable about AES and about Whitebox cryptography and you read those papers, then you can maybe also see where I struggled or what kind of concepts I didn't come up with or didn't think about when looking at this. Okay, so here are my notes again. But let's focus on the first page. You remember this one here from the last video. This was kind of like my breakthrough when I wrote down the input and output of one specific function and realized that it implements the shift row step of AES. So I decided to write down the steps in the AES algorithm. And I kind of wanted to understand each step and maybe think about how they could be obscured or hidden, or how the key could be incorporated into them. I also mentioned multiple times that there are these AddRoundKey steps where the key is XORed with whatever state data this is. So theoretically, if you would find this step in the binary, then we could just extract the key bytes. And obviously this was a first idea I tried. I searched through the disassembly for XOR instructions and checked if they could be the step, but I didn't find any. So next is the SubBytes step. And when you read what it does, it's implementing an S box, a substitution box. Like, it's so simple, but when I first heard about AES, I don't know, a few years ago, and I read S box, that sounded so mysterious and I just didn't understand it. But it's the most easiest thing you can think of. It's literally just a substitution. It's just a defined table of how you substitute one byte with another byte. And obviously there's some theory behind how this S-box is implemented and why specifically this one is used, which I also don't understand, but this is the table. So if you have the input byte 2, 6, you would substitute that one, replace that byte with F7. Okay, so this step can be reversed. I wrote this also down here on the paper. I noted down that the S-box is just substituting bytes, and if you would see 3.9, you can just reverse it back. The next step is the shift rows. And shift rows is what we just had analyzed. So this one function that we've learned about at the end of last video is just how shift rows is implemented. And shift rows, as we know, is implemented in this one function. So it's not obfuscated or hidden in there. So we are kind of looking for all the other functions. Then mixed columns. This one is probably the most mathematical step, and probably also the step I have the most problems with, because I love math, but my brain just doesn't work that well with math. So I can look at the step and I can probably also implement it in software, the step, but knowing how, like the S-box, okay, it's easy to reverse. But with these more complex math operations, I don't have kind of an intuition for, is this reversible, or how easy is it reversible? Is it just a one-to-one match, or is it, do you have to solve kind of an equation system or whatever? Like this, I have more issues with mixed columns, to be honest. But all can be Googled. These are all questions that people have kind of asked already. And you find a lot of resources about each AES step anyway. So, it's all stuff you can read up on. And then we have another AddRoundKey step, which is basically the same thing. It also XORs the key. And then it continues this for multiple rounds of AES. It's not that important. And then comes the last round, which is kind of just like part of the regular round as well. But that one only contains a SubBytes, a shift rows, and the AddRoundKey. It doesn't have a mixed columns anymore. What is not mentioned, especially when you look at the AES algorithm itself, that there's also a key schedule algorithm. So when you look at the high-level description of the algorithm, there's a key expansion. The round keys, the keys that are being XORed to the current 16-byte state of AES, are actually derived from the original key. And they are using the specific AES key schedule. So this is executed in multiple rounds. So for each round, AddRoundKey uses a new different key that is derived from the original key. Yeah, and you can read about how this key schedule is implemented. The interesting fact about this, probably for attack reasons, which I at some point learned about, is that it's reversible. So if you know the state of the last AddRoundKey step, for example, then you can reverse the key schedule as well. So if we would catch any of those XORs at any point in time, then we can just reverse to the key and get the original key. Next, I was thinking, how could you hide or obscure these steps? So we have found shift rows as a functions, but how are the other things implemented? And so I was thinking, can you actually combine certain functions of these in one single function? For example, down here, we have an AddRoundKey and followed by a SubBytes, or depending on how the loop goes. So AddRoundKey will always come before a SubBytes. And we know this XOR, and we don't have a flexible key anyway, so we know each key in the key schedule, right? Because the key is like encoded somehow already into the algorithm itself. So for example, these steps could be combined. You know the byte that is coming in, and then you can basically say, okay, if the byte that comes in is 12, then we know the result of what would happen if you XOR it with the key and then substitute it. So you can implement this with a lookup table. Instead of implementing the XOR directly with an actual XOR instruction, you can make a lookup table, right? For the XOR itself, but also for the combined thing. And this was a big breakthrough for me, the fact that you can use lookup tables for this. So let's have a look at the binary again about those lookup tables. Remember this huge function that we saw? Let's have a quick overview before we dig into the assembly. So we have a lot of move instructions, a couple of load effective address instructions. Here you just add some values and some shift lefts, but that's basically it. That's all of it. So there's nothing complicated here. It's just moving it around. Okay, it's just annoying maybe to read. So you can also set a breakpoint here and step through this and observe what kind of values are loaded here. And obviously that's what I did. So let's use GDB, set a breakpoint at this function and use an input that we would recognize. So we enter the string 1, 2, 3, 4, 5, 6, 7 and so forth. Okay, so we see our trace happening and there we hit the breakpoint. So the first few lines just load some value from some address into RCX and RDX. And you can see that that value, whatever we loaded, will be added to the RAX that we get from here. So let's step until the add. So we can see RDX, which was loaded from the initial value up here, and then RAX from the value here. So these get added together. And when we look here now, RDX is an input pointing into our data that we entered. It might not be obvious, but it's in fact what I have written in the top corner here. So this is after the shift rows step, which means shift rows was already executed, but nothing else happened on our input. So this is still our clear text input that we have entered. So what this tells you is that at the base pointer -hex50 is the current AES state, which is still our input here. And RDX in this case is then, or the values that are loaded here are used as an offset into that state. And this offset is currently 0, so it gets the first character. And then after that, we get a value from base pointer -20, so we haven't seen that one yet, into RDX, and shift left it by 4. And then we add RCX to it, which we loaded early in the beginning here. So let's have a look at these values. So RAX is the character we entered, 1, and we add to it RDX, but it's 0 in this case. So nothing changed here. And then look at this interesting move. We use RAX, so the value of our character, hex31, we use that as an offset into some data. That is a lookup table, right? We can examine this address here as well. So these are just, random looking data. In fact, this is the data that we saw being set up in the very first video where we looked into all this data that is being set up, which we didn't know what it is about. So when I discovered this, I thought I basically got it, right? So we know now there is in fact a lookup table, and in the first round, the first breakpoint we hit, it still operates on our clear text input data that we know. And it just like fetches some values from a huge table. So this was the first attack idea that I had. Because like we just discussed, we could theoretically hide some of these steps in a simple lookup table. So I thought if we extract the value that is being looked up, it is either, the result of the S-box, or it might be the result of the AddRoundKey step, or it might be a combination of both, and all three are reversible. Let's make an example. We have here our string 1 as input. Let's do it for 1 byte. We have hex31. Let's say the output is 73. So if it were 7.3, then we could check it here, and apparently it would be 8F, which doesn't match our input. So it was not SBox probably what was happening. Then we could assume it's SBox plus AddRoundKey, or it's only AddRoundKey. If it were AddRoundKey, we could just XOR. But you know, if you do that and you step through the program and do it for each byte, just wouldn't work, right? But this was my first attack idea that I tried out. So I spent a lot of time on just extracting these kind of values and tried if I can reverse them that way. And I really thought I figured this out. It's easy. I solved it. It's just like one of these reversible things. So let's have another look at my notes, what I wrote down. Here I just wrote down how the AddRoundKey step works. Like I earlier said, you can combine certain steps, and you can also change the order of certain steps, right? Basically, it doesn't matter if you do SubBytes first and then shift rows, or if you do shift rows and then SubBytes, right? You can just reverse these. Doesn't matter. And the same thing with kind of the other stuff. At least I can design or implement the algorithm in a way that I basically mix up these things and then, you know, make the lookup tables accordingly. So I was just like, you know, playing with this idea. So as you can see, I wrote this kind of down. I drew this with these 4x4 matrices, and I kind of wanted to look at one byte. Let's say this is what the function implements here. What happens if I find this byte? Where would that correspond to in the original key, right? Let's say if that is 3.9. A shift rows would just like move it a little bit. Then the SBox. Reversing the SBox is easy, like I said. 3.9 would correspond to 1.2. So, and if that is the result of the XOR between the text and the key, we can use 12 XOR 30 and we would get out the key. And so I was, you know, just exploring how would single bytes change during AES, and, you know, what parts can I reverse. And so I figured maybe these steps together could also be kind of combined. So I was also thinking, if you do the shift rows before you do the AddRoundKey step, you obviously have to just, you know, you can also just apply shift rows to the key itself. You basically do the same there, and then, you know, the correct byte is again XORed with the key. So I was thinking about just different ways how you can mix up the algorithm and change orders and stuff. And this is how I spent a lot of time. I was just assuming, okay, the output I see is the state here. In order to reverse now and get back to the key, what steps do I have to do? Okay, it didn't work. So let's assume the output was from this step here. What do I have to do to reverse it? Or the output was from this step here. Let's try to reverse it. But it didn't work. I never got, you know, the key this way. But I also felt I was really, really close again. Like I was so deep in it already. I spent so much time on it. I was sure that it was just, you know, a few steps away. Then I decided to spend a little bit more time on the lookup tables. What we just learned is that these moves are the lookup tables, right? So basically what I did, I was just going through this huge function and specifically looking at these lookups. What is the index that is used in the lookup table, in this case RAX, and what is the result? What is being looked up from, right? So I was just writing this down. If this is our input text that we want to encrypt, this is basically what you saw in GDB after the shift row step. First, you remember we used some index to get, you know, one of the characters in here, and it was just 0. But if you would step through this, you would see that it's looping slowly up. So in the first run, it was 0 just now. But if you go, you know, a next iteration, if you look how this is implemented, you would see this also with the next column. So we get the first value, 3.1. You saw that. But when we use now the 3.1 in the lookup table, we get a 32 byte value, which is kind of odd, right? We would expect if it's a simple byte lookup thing, the result would also be 1 byte. But you can imagine that it could also be just masked, you know, it's kind of like odd offsets and you always take like the byte here or something like that. But then you continue in that huge function and then you reach the next lookup where it takes the next character from your column, which is 6, which then in hex is 36. And then you add hex 100 to it, you make it 136. And then with A is obviously 41, you get 241, that is used in lookup table. And you get all these 4 32 byte values that correspond to the input text. And that is the first part of the huge function. But that was not all of it. So when I was stepping through, I realized, oh, there's a lot more happening. So then you take the 32 byte result from, you know, the first character and you AND it with just a nibble with F and you get the last nibble here. So you get the 0 here. And then from the second character you got, the second 32-byte value, you also take an F and you get out 3 because, you know, the last byte, the last nibble here is also 3. And then you combine these two. So you don't see it really here with the 0, but the 0 is in the front and the 3 is in the back. It's better visible here with the other two characters, A and F, where you also, you know, take F, the last nibble, so 4 and 1, 4 and 1, and you combine them together to 4, 1. So you get these intermediate values. And basically you do this then again, but this time you shift this 32-byte value by 4, so you kind of cancel out the last nibble. Now the 7 is the last value here, and so you get 7 and the D and combine it. Then you get the E and the F and combine it, right? So you get these intermediate bytes. Then you use these for another lookup at this table with this address here, and you get another value. So the first, so 03 produced coincidentally also 03, or maybe not coincidentally, I don't know. And then the 41 produced 5. And you notice that these again are just one nibble. And here the results of these lookups are A and 1. And these are again combined together, 3 and 5, and A and 1. And then you use these again for a lookup, and you get 6 and B, and combine these together, and this is the final result. This will be the first byte, and this is basically what the huge function is doing. It's doing these lookups. I was trying for the longest time reversing the result bytes here to the original state, because I assumed this is the result of SubBytes, mixed columns, and AddRoundKey. And it just didn't work. I just couldn't find the solution. I spent so much time on it, and I constantly assumed that must be the solution. So I kind of tried to brute force this. You know, I thought it's just a combination of kind of these things. So here's a lookup table to perform the S-box, the substitution. Here's the inverse of it, so that will just reverse it. And then we have some values here to perform the inverse of mixed columns, to inverse that as well. And then I also thought maybe, you know, maybe there's some random XOR in there, some random blinding or so. So I defined a few functions. I kind of used the intermediate values that I extracted and just, you know, tried different combinations of all of these things. Let's try mixed columns together with S-box. Let's try inverse mixed columns with the S-box inverse, you know. And, you know, I'm using all these different kind of combinations that I thought, I don't know which is the right thing, you know, this blows my brain. I can't concentrate anymore. I spent so much time on this. It must be one of these combinations. And it obviously wasn't. You know, I was not able to reverse this state. So I was kind of getting nowhere here. And I was not really able to figure out the meaning of a lot of these values. Like, I didn't understand what these lookup tables actually implement, because I was so sure that I, you know, could reverse the AES algorithm based on this, but it kind of didn't work out. So I thought, let's look a little bit more closely at the lookup table values and see if we can somehow, you know, understand the meaning of these things. So here's basically the same thing again, just displayed as a graph a little bit differently. So the first character 1 is used in a lookup table, and you get these 32-byte values, and the character 6 is used and you get these 32-byte value and A and so forth. So these are then, this is the first lookup table result that is used. And then you remember that you take only these nibbles, combine them together, and use this as a lookup to look up another nibble, and combine two nibbles again in one byte and use it as a lookup for this value. And then the end result is you get again two nibbles that you combine to B6 in this case, and then that is the result that you use. So I was looking at this and trying to figure out what does this mean? Like, what is the result of the first lookup here? These bytes, this 3-5 that is coming out, what is the meaning here? Like I mentioned very early, the holy grail would be to find the AddRoundKey step with the XOR. So I was looking for, is one of these steps here an XOR result that could be our AddRoundKey step, right? And so I was looking at these values and tried to XOR them. Is this maybe the XOR result of these two values? So I was typing this into Python, hex03 XOR 41, and the result is not 3-5. Okay, so this was also kind of leading nowhere. I just couldn't really understand the lookup tables. But I wanted to mention this because after the challenge, when I was chatting with somebody about these implementation of the lookup tables, there was in fact an XOR happening that I just didn't see. It's a bit more hidden. I was looking at this so much and I did not figure out that here is actually an XOR lookup happening. Maybe you take a second and you just pause the video and try to figure out where there is an XOR happening. 3.5 is in fact an XOR result. It just didn't happen as I was thinking it would happen. Because the XOR is happening between 0.4 and 3.1. So there was in fact an XOR. I was just too blind to see it. But that wouldn't really have helped me, right? I assumed this could be an XOR result, and then I tried to reverse, AddRoundKey and whatever, and it didn't work. But I just found this interesting that I was staring at this so much, trying to find, meaning behind this, and there was in fact an XOR result. Now, I spent so much time on this, and it just led nowhere. I wrote these brute force scripts. I tried to, understand how mixed columns works, tried to reverse certain steps, and it just didn't work. And it fairly early already dawned on me that it's not that simple, that they actually implement some stuff to hide the actual result calculations. Why I thought this is actually related to RSA, because this is where I first encountered this, and it, as a concept, it kind of stuck with me, and it's kind of these interesting things that are super logical, but at least I never thought of them myself. And this is the concept of blinding a calculation. Blinding techniques also have applications to prevent side channel attacks on encryption devices. And so the first time I heard about this was in a hardware attack course at university talking about RSA. I don't want to go too much into this now, how RSA blinding works, but if you just look at the equation here, generally if you want to encrypt something in RSA, you would take the plain text and raise it to the power e modulo n. But in this case, you actually multiply the plain text with a random integer r before you do that. And at first it sounds like RSA would then produce something completely ridiculous, right? If you multiply the plain text first with another value, it just completely becomes screwed up. But the trick is then later that you can unblind it again, that you can remove this multiplication by r and reverse this, and suddenly you get the intended value back. How this works, we don't want to get into this, but the idea is that you can do something to a value that only you know about, then you perform your actions in kind of an untrusted environment that could leak, that an attacker could see, and in the end you unblind it again and you still get the correct results. And so in our case, we can imagine that sure, our plain text goes in, but then all the operations are blinded with some kind of secret that we don't really know about. And then just before the output is happening, they unblind it. So all the intermediate steps and values that we have are useless to us without knowing how the blinding was implemented. And this is also kind of where I then gave up. I felt like the beast was too big for me. I spent already so much time on this, and I would have to read the papers, and I was already burned out of this challenge. And I was scared if I would just now try to push myself and continue, I would just get so stressed and would lose all motivation for the challenge. So I decided, okay, it's good now. I spent a lot of time on this. I learned a hell of a lot during this one. I never understood AES to the level I'm understanding it now. And so I'm super happy with my personal learning results, even though I'm really frustrated with this challenge now. So I decided, because I heard that there exists a simple tool that can perform an attack on this, which I don't have to understand, but the tool just somehow works to get the result, to get the flag, and and then basically that's what I did, and we will look at that next video.